My name is Daren Swasey. I'm an electrical and computer engineering student at Utah State University in my senior year. And the project I've been working on over the summer is this really long title, but to shorten it, it's a burglar alarm using GNU radio and the USRP N310. And our goal in the research we've been doing is to be able to secure an indoor area using RF signals. The main intent is to use Wi-Fi, but at the current stage of development, we're using QPSK to prototype and develop those algorithms we need to do that security. The reason we want to work towards using Wi-Fi is because it is available in many, if not every building that you could possibly be in. And it has such a broad coverage and acts as a really good signal of opportunity to grab data from and detect if somebody could potentially be intruding in an environment. And there's two phases to this. The first is intrusion detection, which is what I've been working on. And the second is target tracking, which is a follow-up to once a target may be localized, then we need to find out where they continue to be in that area. So first, we have to figure out how are we going to detect intruders in the first place. And it turns out it's pretty simple, and it's really convenient. So just imagine you have some signal SFT that's going into a channel. That introduces a whole lot of noise and a whole lot of different information that we don't actually care about. It could be motion from people moving around. It could be doors, walls, and windows that introduce attenuation or phase shifts to the signal. And it comes out as a signal X of T. X of T goes into our receiver, and the receiver has a whole bunch of internal tools like the PLL, AGC, simple synchronization to pull out that original signal S of T in order to get the data that you want, so you can get your daily dose of internet cat memes or whatever it might be. And the thing about that receiver is, yeah, it's used to extract that signal, but if it can extract the signal, it can also show us information about what it did to extract that signal. And in doing so, we can find out that information about, is there motion, is there somebody there? And the things I'll be focusing on in the rest of this presentation are the PLL and AGC, because looking at the data that they are able to remove from the original signal, we are actually able to get the most out of that. So to summarize what's going on here, just pretend like your signal SFT is a diamond, and then it gets transported to you in this dusty old box. That dusty old box has a lot to say about what happened as the diamond was being transported. And this is kind of what I think of in this clip when we're looking at this. The box says everything, and that's what we're focusing on here. So in order to find out aspects about that box to use to find intruders, we need to set up some initial tests and do basic evaluation of the data we get from them. Do we even have enough information to run intrusion detection in the first place? So this is the GNU radio flow graph that we used for the majority of the testing. It's fairly simple. The top half is the transmitter, where we use pre-recorded IQ data sent through a QPSK modulator. And on the bottom half, we receive through USRP N310. The signal gets basebanded, filtered, then runs through the simple sync and a PLL. And on the receiver end of things, all of these outputs or inputs can be used for potential file syncs where we can evaluate that data and see if somebody was moving, if somebody was here, does it tell us anything about that? And it actually does. Again, I'll be showing the PLL data later. What we did to test was there were two cases, and the test cases involve the quiescent case, in which there's no intruder present, and the second is the active case, where there is an intruder present. And in order to do that test, I would just walk around these hallways, which have 6 antennas installed in the ceiling to help us collect that data. And in doing these tests, it's a fairly generic baseline to get, can we see any consistency if there's somebody there, if there's somebody not? And this is what the data looked like from the PLL on this next slide. Getting ahead of myself. So here's the hardware we have. So we have 2 USRP N310s. I'll try to use my mouse there so people online can see too. So we have N310s. The first is connected to the transmitter, which comes over here, gets fed through these 2 amplifiers that each amplify at 12 dB. and that's hooked to this antenna here. And it's just set up in our lab room. And in the initial tests, we just transmitted between the antenna here and then the south center receiver from that diagram before. So it's a fairly close range test, which would help us get to more consistent data and evaluate whether or not this is actually going to be possible. And then all the receivers are connected down over here. And as far as hardware goes, I think one of the most important pieces of information on this slide is just we transmitted at 905 megahertz. And these are the results. There's a pretty clear difference. So the top is the quiescent case where I would start the test, leave the building, wait for about 10 minutes, come back in just to get a good baseline of what would it look like when nobody's there. And you can see it's pretty consistent. Nothing's really going on. Whether it's downsampling or some hardware effects, you get a lot of little blips there, but that is irrelevant. On the bottom is the active case where as I was circling the building, you'd get these big variations every time I passed that receiver. So obviously there's something going on and we can use that to detect if somebody's there. But that's not the only thing we did. Obviously these are good results, but at the same time, we want to figure out, is there something else we could use to get better results or something that we can use as a backup to reinforce the data that we have? And it turns out there is. We tried working with an AGC, but the AGC is one of those things that just squelches the data. It kind of removes that the effects of whatever's going on and reduces the amount of information we have. But it does that somehow, right? And the way it does that is by using the gain value, which will bring the original signal back up to some reference amplitude. By modifying about 4 lines of code, I was able to remake this AGC and get that output gain port on the side there, which is really critical to all of the rest of what I've done here. That AGC block was stuck in the receiver side before the signal gets basebanded. If it's not put where it was, the signal actually loses a lot of information due to filtering and basebanding. So it did provide the best results to do it before that. And as you can see, it's pretty similar to the PLL results. It's a lot cleaner for sure, but it's also on a bigger scale. The ratio from the maximums on the active case to the maximums on the quiescent case were way different than the PLL, but it's just, at this point, it doesn't really matter actually how it looks, because this was a very controlled direct path test from that transmitter to the receiver in the ceiling. And so we had to consider what would it be like in a more realistic situation where the transmitters are not just laying out on the floor. So I transitioned the receiver to the southwest corner of the building in the ceiling. And for these results, the transmitter was in the southwest, the receiver was in the northeast. And the reason I did that was because the farther apart the receivers are, the better data you get, because there's less of a direct path and there's more opportunity for an intruder to interfere with that signal in a channel. So on the left is the PLL results. It looks pretty much the same as what it did in the original tests. And that's what it looked like for the active test in that case. Very different. There's not a whole lot going on. There are some periodic variations, but it's a lot harder to tell what they really are. And then there's some random blip. I don't know what that is. And then on the AGC side, we get a huge, huge result. And at this point, we're like, yeah, okay, the AGC needs to stay here. It provided very good results. And in doing that, the next step is to quantify those results and be able to run this in real time. So we need to consider, what can we actually pull off of this signal to use as metrics to run in the real-time processing? This is some data I gathered while walking around the building and stopping in a few locations, moving, stopping again for about a minute at a time, just to see, can it pick up only motion or can it pick up a presence in general? And this is what I got. So the 3 conditions you can see here, the first one in the green box is what I would consider the quiescent case. There's no movement, nobody seems to be there. And then there's the case in the purple box where there's noticeably more variation in the signal, which indicates to me that there's some movement. And then the third condition is in the red box, where there's a lot of variation and the gain went to a different level entirely, which indicates there's also some positional data that we can extract from this. And these all led to 3 detection metrics that can be calculated and evaluated over a sliding window on the signal. Those metrics are the average level and the standard deviation of the amplitude and the energy. And the convenient thing about this is that they all feed into each other when you calculate them, making the calculation steps really simple. Using the standard deviation equation, we can first compute the average level and find mu. And then by finishing off that calculation, we have the amplitude standard deviation. And then that first term in that equation can be used for the energy standard deviation, where that feeds into mu, and then you square that again and finish the calculation. So these 3 metrics provide a lot of information, and they're very closely connected. So it's really quite simple to get more data and evaluate what's going on. So knowing that, I developed some code in MATLAB to highlight the expected results using these metrics, and also developed the process for what would happen in real time. So the program would collect the quiescent data. So say you had 30 or 60 seconds over which a sliding window would run. It would evaluate each of those 3 metrics and run the calculations. And at the end of that period, it would set thresholds. And after that, continuously running, it would evaluate at each sliding window portion, have any of those thresholds been exceeded. And the top piece of data here is just for the amplitude standard deviation, where the pink is what it highlighted using a 1-second window with no overlap. And it caught a good amount of what I would expect it to. And those are pretty good results. Then you add on the level detection on the bottom, and it highlights basically everything. So I was really happy with these. We were able to stick it into GNU radio after we figured that out. And to do so, I made this block called GRRID, which stands for Real-Time Intrusion Detection, which wrapped up all that MATLAB code into GNU radio and was able to perform these things in real time. And in this case, you can set the arming time. So here it's 30 seconds. And you get the window length. You can set overlap if you want a little bit more precise of data, but not have to calculate too often. And this was designed to be used with the AGC because that provided the best data. And in order to run this and actually find whether or not there's an intruder in the environment, all you need is these 4 blocks and then the transmitter, because we had to transmit as well. But just using those 4 blocks, you can learn whether or not somebody's in your environment that you're testing in. These were wrapped up into a hierarchical block that supported up to 4 copies of the receiver module, and we began to run tests. So this is a very simple test. I had the transmitter in the southwest corner of the building again, and the receiver was the south center in this first case. And then the second clip shows a little bit less motion and how sensitive things can really be with the transmitter in the southwest and the receiver in the southeast of the building. So we'll just watch that. So what's going on is I programmed into the RID block some sound-based feedback, and if there was a detection that was met, if there was a threshold that was exceeded, there would be an alarm that sounded. And depending on what conditions there were, it could sound one particular sound, it could sound a different one. It depends on if there were one or multiple metrics that had been exceeded. Unfortunately, we didn't have that going, but so it worked, was the essence of that. And though it did work, I wanted to find out how well does this work, and that involved doing a little bit more testing. And what I did was, in these hallways, I had a Bluetooth headphone connected to the test computer, and with that sound feedback you didn't hear, I very meticulously walked around the hallways figuring out where would each antenna pick up motion or my presence. And here's the results for the south center antenna. Everything highlighted in blue is where it would be able to pick up motion. And it did a fairly good job. It picked up just about half of the testing area. And I proceeded to do this with the other 3 receivers as well and generated this heat map. So the darker areas, all 4 of the receivers were able to detect motion there. And then in the lightest area, only 2 were able to detect it. But these are pretty amazing results. They're very sensitive, and I'm glad we were able to get the results we did. There's a lot to do with this still. So in the future, there's a lot we can do. We can downscale, which essentially means taking this from an N310 back down to something like an RTL SDR. We don't need to use that much power to run this. The sample rate I used for those tests was about 2048 hertz. So it doesn't need a whole lot to run well. And the next goal as well, like I said at the beginning, would be to implement this with Wi-Fi and not have to transmit anything, because being able to passively do that would be a lot more beneficial and be a potential application for in-home use as well. And as a follow-up to me, as what Dr. Moon will be doing here in a minute, this can also lead to target localization as an extension of target tracking. So if you're able to detect the intruder in the first place and use some of that positional data that is potential there that I showed earlier, then you can latch onto that point and then use what Dr. Moon will talk about to follow them. I'm glad I could be here, and I hope you have been able to have a good time.
Thank you very much. Are there any questions at this point?
Hey there. Cool idea. It's probably something anyone here could set up in their house. It seems pretty accurate. Do you handle the geofencing aspect? By just putting a receiver kind of within the area that you're trying to monitor? Is that kind of the idea?
Yeah, that's what I anticipate. It is fairly sensitive. Again, what I mentioned before, maybe I need to be a little bit more clear about that, but the farther away your receiver is from your transmitter, the better things tend to work, because there's more opportunity for interference, if that makes sense. So I believe that would be a fairly simple way to implement in home. It would be quite easy, I believe.
Thank you. Anyone else? Okay. Looking online, did they actually run MATLAB code, or did they convert it to Python or C++ first?
It was straight from MATLAB. So, okay. Let me start that over. I did it originally in MATLAB, but then converted it to C++ to write the block.
Okay, so you're not calling MATLAB from within GNU Radio.
No.
There does exist blocks for that, by the way. They're
Interesting.
A little out of date, but it is possible. Can it detect animals? I need to know when an animal enters my yard.
I don't actually know the answer to that question. We weren't able to get a whole lot of testing done. Most of it was done just by walking at kind of a regular pace. I did do some tests where I brought in my longboard and I'd get down on my stomach and like crawl across the ground, and it does pick up that motion. So I anticipate, depending on the animal and kind of how you set it up, it would be able to pick up that as well.
Okay, Adam, you need to set that up yourself, and we want to know the results. From Clayton, do any false detections occur? Interfering signals, passing cars, etc.?
This was tested in one of the engineering buildings at Utah State, and so it's fairly isolated from nearby traffic, at least. As far as false alarms, it really depends on how you set up the system. With the RID block that I made, you can set tolerances for each of those detection metrics. So it does depend on how you set it up. It's not perfect, and I know that in an overnight test I ran, there were some detections that probably shouldn't have been there. But that's just kind of part of the process. It's a tuning thing, and it's figure out what would be anticipated for your normal environment, and then go from there.
Great, thank you.